June 28, 2026. Today, the world's most powerful particle accelerator, the Large Hadron Collider at CERN, is powering down. After more than a decade of smashing protons together at nearly the speed of light, the great machine is falling silent. For 4 years, it will sit dormant like a sleeping giant as engineers replace kilometers of superconducting magnets and install new focusing systems. When it awakens in 2030, it will be reborn as the High Luminosity LHC, capable of producing up to 100 times more data than before. The goal is nothing less than to unlock one of the greatest mysteries of the universe, the nature of dark matter, the invisible scaffolding that holds galaxies together. But the LHC's shutdown today is more than just an engineering milestone. It is a moment of reflection, a pause in our relentless quest to understand the fundamental nature of reality. And it falls on a day that marks the births of some of the most remarkable minds in the history of physics. Today, we celebrate the anniversaries of 3 giants whose work reshaped our understanding of the quantum world: Goeppert Mayer, Klaus von Klitzing, and Stewart Bell. Each of them, in their own way, asked the deepest questions about the structure of matter and the nature of reality. And each of them, in their own way, reminds us that the most profound discoveries often come from the most unexpected places. Let us begin with Goeppert Mayer, born on this day in 1906. She was a woman who defied the odds at every turn. In an era when women in physics were almost unheard of, when universities routinely refused to hire female professors, when the very idea of a woman making fundamental contributions to nuclear physics was considered absurd, Goeppert Mayer persisted. She earned her doctorate in physics from the University of Göttingen in 1930 at the age of 24. Her thesis was on the theory of two-photon absorption, a phenomenon that would not be experimentally verified until decades later. It was a masterpiece of theoretical insight, and it established her as a physicist of the first rank. But the academic world was not ready for her. She moved to the United States with her husband, the chemist Joseph Mayer, and found herself relegated to unpaid positions, essentially a volunteer researcher. She worked without salary for years, often in cramped and underfunded laboratories, while her male colleagues received promotions and recognition. Yet she never stopped thinking. She never stopped asking questions. She never stopped pushing the boundaries of what was known. And then, in the late 1940s, she had an idea. A simple, elegant, and revolutionary idea about the structure of the atomic nucleus. The nucleus, she realized, was not a random jumble of protons and neutrons. It was organized into shells like the layers of an onion. Each shell could hold a certain number of particles, and when a shell was filled, the nucleus became unusually stable. This was the nuclear shell model, and it explained a host of experimental observations that had long puzzled physicists. It explained why certain isotopes were more abundant than others. It explained why certain nuclei were exceptionally stable. It explained the pattern of magic numbers, the specific numbers of protons or neutrons that conferred extraordinary stability. Goeppert Mayer published her theory in 1949, and it was immediately recognized as a breakthrough. She shared the 1963 Nobel Prize in Physics with J. Hans D. Jensen and Eugene Wigner for her discoveries concerning nuclear shell structure. She was only the second woman to win a Nobel Prize in Physics after Marie Curie. Feynman would have loved Goeppert Mayer. He would have admired her courage, her persistence, her refusal to be marginalized. He would have recognized in her the same spirit that drove him, the insatiable curiosity, the willingness to challenge received wisdom, the joy of discovery. And he would have appreciated the beauty of her shell model, the way it reduced a complex and chaotic system to a simple, elegant pattern. The shell model is a triumph of reductionism, the idea that the behavior of complex systems can be understood by studying their constituent parts. It is the same reductionism that underlies Feynman's path integrals, the same reductionism that underlies all of modern physics. It is the belief that the universe is not random, not arbitrary, but organized according to deep and discoverable principles. Now, let us turn to Klaus von Klitzing, born on this day in 1943. Von Klitzing is a physicist of a different stripe. He is an experimentalist, a master of precision measurement. In 1980, he was working at the High Magnetic Field Laboratory in Grenoble, France, studying the behavior of electrons in a two-dimensional electron gas under extremely low temperatures and high magnetic fields. He was not looking for anything revolutionary. He was simply trying to understand the electrical properties of these exotic systems. But what he found changed physics forever. He discovered that under these extreme conditions, the Hall resistance, the transverse voltage divided by the current, became quantized. It took on discrete values that were independent of the material, independent of the geometry of the sample, dependent only on fundamental constants of nature. This was the quantum Hall effect, and it was a stunning demonstration of the power of quantum mechanics. The quantization was so precise, so universal, that it provided a new standard for electrical resistance. It also allowed physicists to determine the value of the fine structure constant, a fundamental constant that governs the strength of the electromagnetic interaction, with unprecedented accuracy. Von Klitzing was awarded the 1985 Nobel Prize in Physics for his discovery. The quantum Hall effect is a beautiful example of how macroscopic phenomena can reveal microscopic truths. The quantization of the Hall resistance is a direct consequence of the quantum nature of electrons. In a two-dimensional electron gas, the electrons are confined to a plane, and their motion is quantized in the presence of a magnetic field. They form Landau levels, discrete energy states that are the quantum analog of classical cyclotron orbits. The Hall resistance is quantized because the electrons can only occupy these discrete states. It is a phenomenon that is purely quantum mechanical with no classical analog, and it is so robust, so precise, that it forms the basis of the modern definition of the kilogram. The quantum Hall effect is not just a scientific curiosity, it is a practical tool, a standard of measurement that underpins modern technology. It is a reminder that the most abstract and esoteric physics often has the most tangible and profound applications. And then there is John Stewart Bell, born on this day in 1928. Bell is a figure of almost mythic proportions in the history of quantum mechanics. He was a quiet, unassuming physicist from Northern Ireland, a man who worked for most of his career at CERN, designing particle accelerators. But in 1964, he published a paper that would shake the foundations of physics. It was a paper on the EPR paradox, the famous thought experiment that Einstein, Podolsky, and Rosen had used to argue that quantum mechanics was incomplete. Bell showed that any theory that was local and realistic, any theory that assumed that particles had definite properties before they were measured and that information could not travel faster than light, would satisfy a certain inequality. And he showed that quantum mechanics violated that inequality. This was Bell's theorem, and it was a bombshell. It meant that quantum mechanics was fundamentally non-local. It meant that particles could be entangled, that the measurement of one particle could instantaneously affect the state of another, no matter how far apart they were. It meant that the universe was even stranger than anyone had imagined. Bell's theorem was a mathematical proof, but it was also a challenge to experimentalists. Could they test it? Could they show that quantum mechanics really did violate Bell's inequality? The experiments were difficult, requiring exquisite control of quantum systems and careful elimination of loopholes. But over the decades, a series of increasingly sophisticated experiments confirmed Bell's predictions. The most recent, a loophole-free Bell test conducted in 2015, closed the last remaining loopholes and showed that quantum mechanics was indeed non-local. Bell's theorem is now considered one of the most important results in the history of physics. It has profound implications for our understanding of reality. It suggests that the universe is not a collection of independent, localized objects, but a single, interconnected whole. It suggests that the fundamental nature of reality is relational, that the properties of particles are not intrinsic, but are defined by their interactions. It is a deeply philosophical idea, one that challenges our most basic intuitions about space, time, and causality. So, on this day, June 28, 2026, we have three scientific giants to celebrate. Goeppert Mayer, who showed us that the atomic nucleus has a hidden order, a shell structure that explains its stability and its properties. Klaus von Klitzing, who showed us that the quantum nature of electrons can manifest in macroscopic phenomena, in the precise quantization of electrical resistance. And John Stewart Bell, who showed us that the quantum world is non-local, that the universe is more interconnected than we ever imagined. 3 different physicists, 3 different discoveries, but all united by a common thread: the power of curiosity, the courage to question established wisdom, and the relentless pursuit of truth. Now, let me bring this back to the present. Today, the LHC is shutting down. It is a moment of transition, a pause in our quest to understand the universe. But it is also a moment of anticipation. When the LHC awakens in 2030 as the High Luminosity LHC, it will be capable of producing up to 100 times more data than before. It will explore new energy regimes, search for new particles, and probe the nature of dark matter with unprecedented sensitivity. The goal is to answer some of the most profound questions in physics. What is dark matter? What is dark energy? Why is there more matter than antimatter in the universe? Are there extra dimensions? The HL LHC is a machine built for discovery, a testament to human ingenuity and the relentless drive to understand the cosmos. But the HL LHC is also a reminder of the scale of modern physics. It is a 27-kilometer tunnel, 100 meters underground, straddling the border between France and Switzerland. It is a machine that costs billions of dollars and involves thousands of scientists from dozens of countries. It is a machine that pushes the boundaries of technology, requiring superconducting magnets that operate at temperatures colder than outer space and artificial intelligence systems that can select the most promising collisions from billions of events per second. It is a machine that embodies the spirit of international collaboration, the belief that the pursuit of knowledge transcends national boundaries and political differences. And it is a machine that, in its own way, honors the legacy of Goeppert Mayer, von Klitzing, and Bell. It is a machine built on the foundations they helped to lay, a machine that continues their quest to understand the fundamental nature of reality. Feynman would have been thrilled by the HL LHC. He would have seen it as the ultimate expression of the scientific method, the willingness to ask big questions, to build big machines, to take big risks. He would have been fascinated by the technology, the superconducting magnets, the artificial intelligence, the sheer scale of the enterprise. And he would have been deeply interested in the physics, the search for dark matter, the exploration of new energy scales, the possibility of discovering new particles. Feynman was never satisfied with the status quo. He was always pushing forward, always asking the next question, and the HL LHC is the embodiment of that spirit. So, on this day, June 28, 2026, as the LHC falls silent, let us take a moment to reflect on the giants who came before us. Maria Goeppert Mayer, who defied the odds and showed us the hidden order of the nucleus. Klaus von Klitzing, who revealed the quantum nature of resistance in a 2-dimensional electron gas. John Stewart Bell, who proved that the universe is non-local and interconnected. And let us also look forward to the future, to the discoveries that await us when the HL LHC awakens in 2030. It is a future filled with promise, a future that will challenge our understanding of the cosmos and perhaps reveal new dimensions of reality. It is a future that we, the curious ones, the ones who refuse to stop asking questions, are privileged to witness. Go outside tonight, look up at the stars, think about the dark matter that pervades the universe, the invisible scaffolding that holds galaxies together. Think about the quantum entanglement that connects particles across vast distances, the non-local reality that Bell proved. Think about the nuclear shell structure that Goeppert Mayer discovered, the hidden order within the atom. And think about the HL LHC, the machine that will probe these mysteries with unprecedented precision. It is a machine that embodies the spirit of Feynman, the spirit of curiosity, the spirit of discovery. And it is a machine that will, in the coming decade, transform our understanding of the universe. Stay curious.